Alrighty, welcome back to 353. Light again, I guess still midterms, fun. So, we get to talk about locking, which is unfortunate that no one else is here today because, again, this is one of the harder topics. So, let's start by ridiculing Java. So, there are some things called monitors that are built into some languages. So, back when someone come up with Java and object-oriented languages and object-oriented programming, developers wanted something easier to use than a mutex. So what they thought to implement is they're like, oh, okay, well, let's just let the developer mark a method as monitor and then let the compiler handle the locking for us. So this means that an object can only have one thread active among all of its monitored methods. So basically, what this does is the compiler will create a mutex for you, one per object, and in every method, the compiler will insert a call to lock at the beginning and unlock right before it actually returns. So in Java, this is how we could do it. We could create a class to model our account. Our account has a balance, and then we write two methods to deposit and withdraw. And because we don't want any data races or anything like that, assuming that multiple threads can be using this account, well, we might have a data race on balance because balance plus equals amount or balance minus equals amount means we are reading and writing to that variable balance for this object. So if multiple threads are doing this, we may have a data race, in which case to prevent it, we have to use mutexes or make sure there's mutual exclusion. So in order to do it in Java, I can just slap on the synchronize keyword on both of these methods, and I have to make sure that it's every method that may have a data race in them, and the compiler will transform it to this. So it will create a monitor, which is basically a mutex, and insert the calls to lock and unlock for us. So we can't be any more fine-grained than that. Every object will have exactly one lock, so if you had multiple fields you want to protect, too bad, it's just serializing accesses to an individual object. So, yeah, and also back when I was learning threads, they just said, hey, you can use threads, and if things start to go weird, just slap synchronized methods onto your code and just wait for it to work properly. So that was great. I had no idea what the hell was going on. So now you know that it's basically a mutex. So our last synchronization primitives is something called a condition variable. That behaves a lot like a semaphore. So the way I like to think about it is a condition variable is kind of poorly named. It's meant to help you implement a condition variable. I like thinking of it as just a queue, so it's a queuing system. So the type is called pthread_con, short for condition variable _t, and it has an init and a destroy, as we saw with mutexes and all of that fun stuff. The only difference is it has a few different methods. So it has a signal, so signal will wake up a single thread on this queue. Again, I like to think of this cond as just a queue. So signal will wake up a single thread, whatever is at the front of the queue. Broadcast will wake up every thread and unblock every thread that is currently sitting in the queue. And then wait is how we put ourselves in the queue. So we wait, we would add ourselves to the queue given by the first variable here. And then to pair with this condition variable, we also need to pair it with a mutex for several reasons. One, you have to call this wait function while you have already acquired that lock, because, well, you probably want to protect whatever condition you're waiting on, so that will be some condition you write in your code that is going to be changing some variable. So you're going to have to access it with a mutex to make sure there's no data races, and also it will need a mutex to add itself safely to the queue, and also, it needs a mutex to reacquire it when it wakes back up. So when it goes to sleep in the queue, it will unlock the mutex, and before it returns from wait, when it's woken up, it will reacquire the mutex. And then if we want a version of wait that will just wake itself up, we can use timed wait. So if the timeout happens, if it doesn't get woken up by a signal or broadcast before then, it will just wake itself up. So the main point is the wait adds this thread to the queue. Signal wakes up one thread, which is whatever is at the beginning of the queue, and broadcast wakes up every single thread in the queue. So, like I said, they have to be paired with a mutex. Any calls to wait must already hold the mutex. You don't need to do it you don't have to have the mutex acquired for signal and broadcast. They just unblock a thread, and then they can go ahead and reacquire that mutex. So again, like I said, why? Well, just remember that wait needs to add itself to the queue safely, have no data races. It needs that mutex as an argument to unlock itself before going to sleep, otherwise no other thread could make progress. And it will also have the rule that the thread will hold the locked mutex after the call completes as well. So after it gets waken up, it will reacquire it. So in both cases, you can assume before and after the call to wait, you have the mutex acquired. So when you write this, you can also have it that one mutex can protect multiple condition variables. Generally, your mutex is protecting data races to some variable, and you're checking some value of that variable. So for this, we'll just consider calls to wait and signal. You could imagine broadcast when we're done. So the wait call, again, does not contain any data races. So you need to understand what wait does for condition variables. So again, the thread calling wait does three things before it gets blocked. It adds itself to the queue for that condition variable. It unlocks the mutex, and then it blocks itself, so it's no longer able to run. Then the thread calling wait needs another thread to return from wait to either call signal or broadcast. Then if it gets unblocked and it's selected to run, well, it gets unblocked, so it can now schedule to run. And then before it returns from that wait, it will reacquire that mutex again, and wait will only return once we have acquired that mutex. So if we were to change our producer-consumer example to use a mutex instead of a center-for, we could create two queues. Like before, we had two center-fors. We had one that was counting the number of filled slots, one that was counting the number of empty slots. So we could do the same thing with condition variables, but our condition is going to be kind of shared between both of them. We're going to have a single condition that is keeping track of how many filled slots we have. So if we have n filled slots, so like the size of the buffer filled slots, it means we have to wait until there is at least one empty slot. And then similarly, if the number of slots filled is 0, then we have to wait until there is a filled slot. So in the producer, instead of having the center-for wait and post and knowing the initial condition, knowing the initial value, I can instead change my code to this. I can lock that mutex because I'm going to be reading the n filled field. So I can put it in a while loop. So while the number of filled slots is full, I would put myself to sleep in this has empty queue. So this is every thread that is currently waiting for an empty slot. If I were to break it out of this loop, either by returning from wait or the fact that all the slots are not filled, I can fill the slot, increment the number of filled slots, which is safe because I still have that mutex, and then I can signal a single thread in the has filled queue if there is one. So if there's nothing in the queue, signal will do nothing. Otherwise, it will wake up a single thread, which is good because I just filled a single slot. Then we can unlock the mutex. And then similarly, in the consumer, lock the mutex, have a while loop while the number of filled slots is 0. We're waiting for a filled slot. If we break out of that, we have the mutex acquired. We can empty a slot, decrement the number of filled slots, and then signal exactly one thread that is waiting for an empty slot, and then unlock the mutex, consume the data, so on and so forth. So do we like this better than the mutex version, or sorry, the center-for version? Up to you. They're equivalent. I would argue that this is a bit clearer what the condition is. Like I'm waiting for all the slots to be filled and then none of the slots to be filled. While for our center-for, it really depends on the initial value in order to be correct. So they're equivalent. You can write one in terms of the other. You should just write whatever is more clear. Generally, if it is something that is changing some more complicated variable than an int, you definitely want to use a condition variable. Otherwise, you can use a center for, kind of up to you. All right, so now we get to have issues. So let's say we had this as our implementation. We have 2 threads running, and we want thread 1 to acquire the mutex, and it is going to run while not conditioned. So let's assume we have a global variable called bool condition, which is currently equal to false. And then the way we've written thread 1 is we have written thread 1 that if it reaches this line here after the while loop, then the condition, then the condition must be true. And then in thread 2, all it will simply do is modify the condition and then signal that, hey, another thread can run. So we need to identify the issue for this. This is, kind of the problem we always have. So how I like to do this is to find the issue. We have to come up with some interleaving between thread 1 and thread 2, such that, in this case, thread 1 executes this line when the condition is equal to false. So how I like to model it, again, we start off, say we have 2 threads, thread 1 and thread 2, each set up to execute these little snippets of code. And then I have the global condition, which I assume is initially false. And then for this, I also like, here, let's move this. So we'll move it to the side. So we have our global variable condition that's equal to false. I also like seeing, as I'm going through it, which thread currently has the mutex, and then what my state of the condition variable is, which I like to model as just a queue of threads, and initially it is empty. So I'll leave you to fix the issue with the following code. I'll show you what should happen. So what should happen is, or in one case where something good happens, is thread 1 executes. It acquires that mutex. So it has acquired that mutex. So now we have thread 1 with the mutex. Oops, let's change the color. So we have thread 1 with the mutex, and it keeps on executing. It checks the condition. Currently, it is false. So it goes into here, and it calls pthread wait. So as part of wait, that will go ahead and add itself to the queue. So it will be on the queue, and then also atomically unlock the mutex when it's blocked. So now it unlocks the mutex and has went to sleep. Now, since it's blocked, only thread 2 can execute. Thread 2 would go ahead, change that condition from true or from false to true. Then it's the only thing that can run. So it will run pthread signal, which what signal will do is go ahead and wake up thread 1 in the queue. So it can execute. Now, if thread 1 is picked to execute, before returning from wait, it has to reacquire that mutex. Right now, no one else has that mutex. So thread 1 can go ahead and reacquire that mutex. So now it's acquired by thread 1. Thread 1, in this case, would go back up to the while loop, check the condition again. Oh, OK, now it's true, so not condition is false. So it would run this line with the condition equal to be true, like we wanted, and then unlock that mutex, and we are good. So that is the happy case. So take a minute and think about a sad case. So we execute that line in thread 1 such that the condition is equal to false. or thread 1 just never wakes up again, which I think is the issue. I don't think it can actually run that while the condition is true in this example. Actually, I should have left that up to you. I should have given you any hints. So, give you a minute to think about that. All right, I have one response from Discord already that says, maybe if T2 modifies the condition to true beforehand, so we start off, T2 executes condition equal to true. So changes condition equal to true, and then it continues or not, or we switch to a different one. If it does signal, it would do nothing. And then we switch to thread 1. So thread 1 would acquire the mutex, which is fine. Check the condition. Well, it's true, and it would just skip here and run this line while that condition is true, which is great. That's what we want. So rewind again to the beginning. Anyone else with an interleaving between these two threads where something poor happens? Yeah. So that's what we just went over. If thread 2 runs first and changes the variable, the condition from false to true, and then signals and nothing's in the queue, it just does nothing, that's fine. Yeah. So signal will wake up at most one thread. If there's nothing there, that's fine.
But what if T2 makes the condition true and then T1 immediately blocks it?
So if T2 makes the condition equal to true, and then T1 immediately locks it, so it acquires that mutex. And now what?
Because then the T2 can't execute, T1 is the only one that can execute, so it goes through the code. The condition is now false as well, not condition. It won't go through the while loop and it just
Yeah, which is fine. So if T1 executes, this is false, and then we're executing this line with the condition being true, which is exactly what we wanted, right? So that's not bad. And then T2, if it executes, it can call signal. That's fine. It would just do nothing. So that's fine. Rewind again. Any other interleaving of this that causes bad?
Maybe the mutex logs first.
So T1 goes first. So always with this, we like to just say which thread executes first. So T1 executes first. It grabs the mutex. So T1 has it. Yep.
Now, I guess it cannot finish.
It
It just continues in T1.
So do you want T1 to go again? So T1 would check the condition, it's false, and then it would go into the while loop. Now what?
I guess wait.
This is close. We're about to have badness happen. Anyone else see it? All right, I guess we don't have the power of numbers. All right, so this is good where we are right now. So currently T1 has that mutex, right? The condition is false, and it's about to call wait. So it's about to add itself to the queue. So a bad thing that could happen is right now T2 executes. So T2 executes, changes that condition from false to true. So now it's changed that condition from false to true. It was allowed to do that. It didn't need to acquire the mutex or anything like that. And then it could continue. It could call signal. That's fine. There's nothing to wake up right now. There's nothing in the queue. So T2 is done. Now if we switch back to thread 1 is about to call wait. And remember what wait will do. Wait will atomically give up that mutex or unlock it, and then add this thread to the queue. So T1 is now in the queue. It is in the middle of this wait call. Is anyone going to wake up T1? No, it is now comatose, right? So this is something bad that could happen in this case, because essentially we had a data race on that condition. So how would we fix it so that this does not happen?
I had a question.
Yeah.
So if T1 gets the mutex, how can T2 then execute?
So the question is, if T1 gets the mutex, how can T1 execute?
T2 execute.
How can T2 execute?
T2 can then change the condition from false to true right before T1 calls wait. But if T1 hasn't called the wait yet, then it still has the mutex. So
So
it's locked.
where in thread 2 does it try and lock the mutex?
Well, isn't it when you block with the mutex that nothing else can execute except for the thread?
Nope. Yeah, so the question is, isn't it the case where if you lock a mutex, nothing else can execute except for that thread? Answer to that is no. Only one thread can execute the critical section between the lock and the unlock, but other threads can still run whenever. Yeah.
So if we had, like, if you tried to lock the same mutex in thread 2, would that fix it?
Yeah, so to fix this, we had a data race on condition, right? So two threads were accessing the same location, condition, the value of condition, and at least one was a write. So thread 2 had a write. So that means we had a data race. It means to prevent that, we need to make sure that all of the accesses to that value are protected. So to fix it, we would need to essentially put a lock to the mutex here, whatever, it's an ampersand, and then what about the unlock? Where should I place the unlock call? Should I do it at the end or right before right after I change the condition? Before? So we could do it before. Turns out it doesn't really matter. But now, if we do something like that, let's rewind again and see what would happen. So if we do something like that, rewinding, and yeah, the Discord comment is correct because, well, we weren't protecting it with the mutex before. So we could swap over right after we check the condition in thread 1. So let's see what would happen now. So with our lock and unlock now, what happened that was bad before was T1 started executing. In this case, it would call lock. So it would call lock. No thread has the mutex, so it would acquire it and then pass through. So now T1, the way to think about the mutex is it is the only thread that can execute any critical section involving mutex right now is a good way to think about it. So now T1, well now T1, what we had before is it continued, it checked that condition, it was equal to false, so it went into the while loop right here. And then what happened bad before was we context switched at that point. So the context switch can still happen, but the mutex should save us, right? So if we context switch to thread 2, it tries to call lock on mutex. Well, thread 1 already has acquired that mutex, so it would get blocked there, right? It would wait and only unblock when it could actually acquire that mutex. So we can't switch to it right now. Well, we can switch to it, but it'll get immediately blocked because the first thing it's doing is trying to lock that mutex, which is already held by thread 1. So now we have no other choice but to execute thread 1. Thread 1, which we didn't have before, we could have executed T2, but now we can't because of the lock. Now T1 executes, and it hits wait, so that atomically gives up the mutex. So it unlocks the mutex, and then it also adds itself to the queue. So now it is blocked, nothing else can run except T2. First thing T2 is going to do is acquire that mutex, so it would hit that lock, it's still doing that lock mutex call. Now it can actually pass it because thread 1 has given up that mutex. So it can acquire that mutex, set the condition variable, or set the variable we're using as a condition variable. Again, this name's kind of bad. We can go ahead, it would go ahead, set it equal to true, and then it would unlock that mutex. So the next line is unlocking that mutex. So unlocks the mutex, and then it would wake up, it would signal, which would wake up thread 1. Thread 1 wakes up, it would reacquire that mutex before it returns from the wait. And then it would go back, check the condition again. Oh, now it's true. Now it can execute this line of code when the condition is true. So everyone okay with that? And also it would work if we put our unlock here as well, right?
So the wait function automatically releases the mutex?
Yes, yeah. So the wait function will atomically release the mutex, add itself to the queue, and block it, all in 3 steps. And when it's unblocked again, before it returns from wait, it will reacquire that mutex. So that's why it's safe, also safe to put the unlock here after the signal, because if we rewind a little bit, let's rewind to when it actually, so when it was in queue and T2 had the mutex, if we instead changed this unlock to happen after the signal, well, what's going to happen is it will call signal, which unblocks thread 1. So it is now in the queue. It could be scheduled to run, but now if we schedule it to run, as part of returning from wait, it has to reacquire that mutex. So it can't return right now because thread 2 has that mutex. So it's slightly better for performance. It doesn't really matter if you have the unlock call before the signal, but it's not going to hurt anything. So in this case, even though thread 1 is unblocked, it's returning from wait, and it will only do that when it can reacquire that mutex, so it can't make any progress now until thread 1 gives up that mutex. So only choice is to have thread 2 go ahead, unlock that mutex, and then thread 1 can now reacquire that mutex, and then it returns from wait. Would check the condition again. It's true, so it would execute this line with it true. Yay, Bob's your uncle. So everyone good with that? Yeah.
Can we call wait without locking the mutex, or does the mutex have to be locked?
Mutex has to be wait to, or mutex has to be locked to call wait. Yeah. All right. So what about, I will pose this to you. What about if I'm trying to be clever and optimize my code? you'll notice that in this case, right, when I came back after waking up from wait, the condition was true. So am I allowed to do something like this? Instead of while, let's write if. And yeah, the Discord comment, unlock after the signal is slightly more performant. No, unlock before the signal is slightly more performant. All right, is if okay?
In this case, I think it is.
Yeah, in this case it actually is, right? Because I only changed the condition from false to true. But what if we have something more complicated? In the general case, you probably have something like this. The condition probably bounces back and forth between thread 1 or between true and false. So we could have the case where we have more threads now. So we have thread 1, we have thread 2, and then we have thread 3. So if we change that while to an if, is there anything bad that can happen here? And remember, this line of code should only run if condition is true. So initially we can have bool condition equal to false. We have a mutex, which is currently not held by anyone. Then we have our condition variable, again, which I like modeling as a queue. Yeah?
So T1 runs until it waits.
Yeah, okay, so first we can have T1 run. So T1 runs, it would acquire that mutex. So if we were to argue about anything else, right now, T1's the only thing that can even continue executing, because first thing T2 would do is call lock on the mutex, can't get it. Same with T3. So T1 executes, it goes ahead and checks the condition. It's currently false, so it calls wait, which would atomically put itself in the queue. Let's just move it. Put itself in the queue and also give up that mutex. All right, now what?
Now T2, except the last line.
So T2 runs except for the last line. So T2 runs, it would acquire that mutex. So T2 has acquired the mutex. It changes the condition from false to true. And then it unlocks the mutex. So now it doesn't hold that mutex. Now what?
T3.
Now T3 executes. So it acquires that mutex. So T3 acquires the mutex, changes the condition equal to false. And then it unlocks the mutex. So it unlocks the mutex. So now we have no choice but to continue thread 2, because thread 1 is blocked, and thread 2 is going to call signal. So signal will unblock thread 1, so it will remove it from the queue. Now there's nothing else to execute except thread 1. So thread 1 will reacquire that mutex in order to return from the wait. And then it goes ahead, and because it's an if, it drops out, starts running this line. Oh no, it's running it when the condition is equal to false. We have royally screwed up. So in general, do not try to be cute. Sometimes you are allowed to get away with if, but typically your program will change and you probably won't be able to get away with it forever. So don't try and micro-optimize your program. Just put a while when you are checking the condition. There's also a few other things where it's actually not guaranteed that when you call wait, you only get waken up from signal. You could get woken up at any time for any reason, technically, if you read the documentation. So that is just to say, always put it in a while. Otherwise, you could lead to something bad happen. All right, cool. So, like I said, condition variables serve a very similar purpose to semaphores. Semaphores are basically a special case of condition variables. You can just create your own unsigned integer, go to sleep or wait when the value is 0, and then when it's greater than 0, you can wake up and actually decrement it. You can also implement one using the other. However, it can get very messy, very quick. That is meant for theory, not for writing clear and concise programs. So for complicated conditions, basically just use condition variables to make your program a lot more readable. So next thing we have to talk about is locking granularity, which gets into performance a bit. So that is the extent of your lock or how big your critical section is, because the bigger it is, essentially you're serializing that part of your code, so it will be slow. So you need locks to prevent data races. If you lock large sections of your program, that's something you can do, or it'll just be slower. Another thing you can do in order to make it more performant is divide the locks, create more locks, and make your critical sections as small as possible. So for example, you might be thinking, oh, what if I want to parallelize a hash table? Well, it probably has some data races in it. I could just lock the entire thing, probably not that good, or I can make it more fine-grained. And guess what? You're doing that for Lab 5. Joy. So you're just, basically it will be like 5 lines of code for that part of Lab 5. Where you're just parallelizing a hash table, you're just adding mutex calls and seeing what their performance is like and making sure it actually works. So things to consider about locks is the overhead of the locks, because, well, even if you create them, they take up some memory. Calling lock and unlock is not instantaneous, so there'll be some overhead there. You've contention, so that is the amount of threads all fighting over the lock at once. The more contention, the more serialized your program will be. And then deadlocks is a condition where we have to think about if we have more than one lock. So again, for locking overheads, they take memory, they take time to create, destroy, acquire them, or lock them, or unlock and release them. And the more locks you have, the greater each cost is going to be. If you optimize your program and you have 1 trillion locks, well, even if they only took up the size of an integer, you're wasting a lot of memory just for that. Not to say any performance overhead of that as well. So the main thing we're concerned about is deadlocks. So you do not want deadlocks. The more locks you have, the more you have to worry about deadlocks. So for a deadlock to occur, it needs 4 conditions. They all have to hold. The first is mutual exclusion, which of course we're only going to worry about deadlocks for things like mutexes that of course have mutual exclusion. So we can't do anything about that condition. 2 is hold and wait. So I have to have a lock and then try to acquire a different lock. And then 3 is no preemption. You can't just force someone to unlock their mutex. You can't just take it away. So we will consider all of our locks are not preemptible, so this condition we will not be able to do anything about. And then the 4th is circular wait. So you're waiting for a lock held by another thread or process. So all of these conditions have to hold. We can't really do anything about condition 1 and 3. And so we can really only do anything about condition 2 and 4. And all of these conditions have to hold. So if we break just one of these, we can prevent a deadlock. And again, we'll have more fun with this when we do some examples and run a successful bank. So here's a simple deadlock example considering 2 processors or 2 processes trying to get 2 locks or 2 threads. It doesn't really matter. If in thread 1, I have 2 locks, and then I try and get lock 1 and get lock 2, and then in thread 2, I try to get lock 2 and then get lock 1. Well, what could happen is thread 1 acquires lock 1, and then we context switch over to thread 2. It acquires lock 2, and now we can't make any progress. So thread 2, the next thing it wants to do is lock 1. It can't get it because thread 1 is holding it. And then thread 2 can't make any progress because, well, it's trying to get lock 2 and thread 2 has it. So neither can make progress anymore. Deadlock is just another word for saying no threads can make progress anymore. They are now stuck. So one way we can do that is ensure order to prevent deadlocks. So if this was our code and we always locked lock 1 before lock 2, then this would never ever deadlock because, well, whoever gets lock 1 is now pretty much guaranteed to get lock 2 because they always acquire it in the same order. So this will prevent that circular wait. So there's no circular wait here. As soon as I have any circular waits where I can form, any type of cycle in the graph, if I was to draw out the dependencies, then you could have a deadlock. So this will not deadlock. I'm using multiple locks. If I always acquire them in the same order, I am good. The other way is to break, hold, and wait. So we can do that using like a try lock. So for P threads, there's try lock, which we haven't used. That's the non-blocking version that tells you whether or not you have acquired that lock. So what I can do is, if I can't guarantee an order between threads for whatever reason, I can break, hold, and wait. So what this code will do is this protected code needs to have both locks acquired. So what my code's going to do is lock a single lock, so lock 1, and then try lock on lock 2. So if it returns 0, that means it's successful. It would go ahead, break out here, run the protected code. I would have both the locks. That's all good. And then if I don't acquire lock 2, to break, hold, and walk, I have to give up the original lock I acquired. So I have to give up lock 1, and then I can do something here like wait, yield, hopefully make something else make progress. Because at that line, I now acquire no locks. Something else can make progress. And then before trying to get lock 2, I reacquire lock 1. That will make me wait until I actually get lock 1. Then after I get it, I try to get lock 2 again. And if I don't, same thing happens. If I do, I run the protected code with both locks. So this is another way I can go ahead and break the deadlock. So questions about that? Cool. All right. So we explored some more advanced locking. We have another fun tool to ensure order. They are called condition variables. They kind of have a crappy name. They're basically a queue. You're supposed to use them in order to express complicated conditions with your variables. They are not themselves a complicated condition with your variable. Again, just think of them as a queue. So they're a lot clearer for more complex condition signaling. And when we actually go ahead and use locks, your locking granularity matters for performance reasons. So how big are your critical sections, which is one reason if you're using Python, or historically why Python has been so slow, is because they just have one big lock around the entire interpreter. So the entire Python interpreter doesn't have any data races, but it is essentially serial. So using threads in Python generally will not give you any performance because they have the GIL, which stands for the Global Interpreter Lock, which, as you might think, is a big lock around the entire Python interpreter. If they break it up, I think the current latest, like Python 3.13, has finally broken that. So they have a whole bunch of different locks now with smaller granularity than just a big lock. And the Linux kernel back in the day, before multiprocessing systems, had something called, I forget what they called it, just the one big lock that they locked everything with. But now, since we have multiple cores on our machine, we want things to run in parallel, so our locking granularity actually matters. And if we introduce multiple locks, we now have to prevent deadlocks. So with that, we are done for the day. I will stick around for a few minutes just in case there's any questions. But just remember, pulling for you, we're all